Okay. In our last session, we're just looking at k-means, right? What exactly k-means is and how the geometric intuition, behind k-means. And in our last class, we were just looking at a scenario where I could have my data points like this, and I have data, and I get my data points like this, right? Then I get some other points here like this. And I get some other points here like this. So the first thing is that I get a random value for k. So if I assume k equals to 3, k means k refers to the number of clusters, as we had already agreed, number of clusters. And if k equals to 3, we come here and we assign 3 random values for the centroid. So this will be 1, 2, and 3. And then we calculate the distance of each point to the centroid. So we can say that this point goes to this one goes to this one, and then let's say this one goes to this one. So we might end up with 3 clusters. So then we change the value of the centroid and we assign, after changing the value of the centroid, we assign value points. This was just a highlight of it, but then we talked about get the value of k, which is random. We said there is a method to get the best value of k, which is the elbow method. So how do we get to the elbow method? We said for the elbow method, the elbow method is a plot of WCSS against k. What is WCSS? Let me show you. I don't keep that definition in my head. And the full meaning WCSS. WCSS k-means. It stands for within cluster sum squares. Within cluster sum squares. So how do you calculate WCSS? Let me show you how it is calculated. It is also called the inertia. It's also called inertia. It is also called the inertia. So how do you calculate that? Let's just quickly look at how that is calculated. It's very simple. Oh, okay, supposed to be here and then I'm here. So how do you calculate that? Let's assume that you have a cluster like this. And so in this cluster, we have how many points? Let's say 5 points. Let's say the points are 2, 4, 6, 8, and 10. What we're going to do is that we are going to calculate the centroid, which is going to be the mean of this point, which is 2 plus 4, 6 plus 6, 12 plus 8 is 20. That's 30 divided by 1, 2, 3, 4, 5, which is 6. So this is going to be the centroid, which is 6. And so the WCSS within cluster square mean is the distance from here to here, 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 squared. So it's like the Euclidean method. This is how it goes. So let's call this position, which is the central, let's call it C. And the distance, let's call each point Z1, Z2, Z3, Z4, and then Z5. So the WCSS will be equal to Z1 minus C magnitude, or you can take the square, which we are using the Euclidean method. You know, go with this one. Let me cancel this one. So we do Z1 minus this plus Z2 minus C squared plus Z3 minus C, or the squared plus up to the last Zn minus C, all that squared, all the square root divided by n, right? So this is the formula for WCSS. I think we can see that online. Let's see how the formula looks like. Then we can open it here. And we can quickly see whether there is. Okay, this is it. Updated, replace. Okay, this, blah, blah, blah. Okay, look at this. Yeah, either using the magnitude square, this they're just talking about if it is less than or equal. So let's look at the one where they actually calculate. This is it. So you have the summation. All over SI means the total number of, you see, we are moving from X to the total number of points, and then you take the magnitude square. So the magnitude of this square, I don't know why they're taking magnitude, because if you square it, it's still going to be the same. So if you square, because the idea behind magnitude is that if there's a negative number, you take care of it. But if you still square a negative number, you still take care of it either way. So this is the formula for the Euclidean, for the WCSS. Let's see whether there's another thing here that we can just quickly pick. Please let me explicitly look for WCSS formula and see some WCSS formula. I don't see a square root on that one, but I was expecting a square root there. Oh, let me see. Don't want advert please. Okay. When they use double magnitude, does it mean square root? I don't know. Because they keep using double magnitude. I think they are just using that as the square root. Let me see. Does double magnitude mean let me see what that means in a deep dive. K means double magnitude supposed to be divided by the vector norm double absolute value. Use this. I want to see why they are using the magnitude sign double there. Let me see what I can. Why does the vector norm use double absolute values? There. So why is it that norm of vectors written as a double absolute value sign instead of a single one? That is, why is it the norm written as this and not this? I think it's appropriate enough. Why such emphasis on this? I think it's rather natural to interpret the absolute value of a vector is learned in complex analysis. Let me get this from a direct source, something like an AI model that will just give me a straight answer. I don't have time to read in literature online. Okay. Historically, it's just a historical thing. Crazy stuff. Okay. So this just takes the absolute without the square root. Why would it take the absolute square? Still, okay, they say the mean square. Okay, yeah, makes sense. So I just wanted to come back to the formula of WCSS, and I just wanted to confirm So according to what we have WCSS being equals to, again, I'll just use, instead of using summation so that I don't confuse all of you, I'll use D1 minus C. They use absolute square plus D2 minus C absolute square, which again, mathematically, absolute square, like, I don't know, D3 minus C and then absolute square. The reason why I'm wondering is because why they put absolute, put square, and then they won't put double absolute, simply because if I have -2, all these squared, it becomes 4. And if I have -2 absolute, it becomes 2, right? And then you put square, it becomes 4. So either you put -2 squared or -2 absolute, something like that, rather than, I mean, just looking at it from the mathematical standpoint. And then all of these divided by the total number of points, maybe, and I don't know how many points are there. This should give the WCSS. So if you have 5 points, and this is your centroid, this is 1 point, this is another point, this is another point, this is another point, and this is another point. The distance from this point to this point, the distance from this point to this point, the distance from this point to this point, the distance from this point to this point. This distance is summed together divided by the total number of points squared, gives you the WCSS. Each distance squared divided by a sum of each squared distance divided by the total number of points gives you the WCSS. So that's what we are saying. And now we are talking about the elbow method. So the best way, let me just remind ourselves. Let me clear this. Now, I said when we want to get the best value of K, we use the elbow method. The elbow method. Now, and I'm saying that the elbow method is a plot of WCSS against the value of K. So WCSS, which is what we already agreed, which is the mean cluster square sum. Now, when we talk about WCSS and then we talk about K, now I'm just thinking, what will be the relationship between K and WCSS? Is it going to be like a positive, like if K is increasing, WCSS is increasing, if K is reducing, WCSS is reducing? For us to answer that, let's just imagine a cluster. Let's say I have in my data, I have IQ against marks, the marks of the student. Let's assume we had just 5 points, 1, 2, 3, 4, and then let's say 5. To just plot that, plot a graph of marks against this on your chart, right? Now, if you plot that, let's assume we're going to have a plot like this. If you do that, a marks against IQ, and we have 5 points, we'll have 1, we might get something 2, 3, 4, and maybe 5. Now, the question is, how many clusters, I'm going to throw this question back to you, and I'm going to ask how many clusters can we get from this number of points? How many possible clusters can be made out of this? Maximum possible clusters can be made out of this. Let me get the input from you. Somebody should say something. Anybody? How many possible? Pardon, Dr. Tony?
2 clusters.
5 clusters.
Okay, Dr. Tony says 2, best man says 5. Who has another option? How many possible clusters can you get out of all of this? We have 5 points. So how many possible clusters can you get out of this? Of course, the answer is we can get up to 5 clusters if we decide to make each point a cluster on its own, right? Because your cluster can either have 1 point or more than 1 point, right? It's okay. So let's take the situation where, so you cannot say your data points are 5 and you say you have 6 clusters. It doesn't make sense. So your K value it should always be less than or equals to n, which is the total number of records you have. So you cannot have the value of K exceeding your total number of points. And if k is equals to n, that means in each cluster has just one data point in your data. That means if your records have at 200, that means you set the value of k to equals to 200, right? So let's assume, let's come to this case now. Let's look at this case. Assuming our data has 5 records as shown here, and we decide to make each cluster constitute 1 point. So this is one cluster, another cluster, another cluster, another cluster, and another cluster. Now, let's calculate the WCSS in this case. What will be the WCSS? The WCSS, remember the formula for WCSS is D minus C magnitude squared divided by the total number of points in that cluster N. So in this case, what will be D minus C? This point, assuming this point was 3, what will be D minus C? It will be 3 minus 3, something like that, and it will be 0 divided by 0 squared, of course, divided by the total number of points, which is 1. Who disagrees?
Not understood.
If it's 1 point, if I say, what is the mean of 2? What is the mean of 2? If I say 2 and 3, the mean is 2 plus 3 divided by 2. Is that correct?
Yes.
Correct.
The centroid is the mean of the points. And so if I have just 1 point, which is 2, what is going to be the centroid of 2? It's 2. Is that correct?
Yes, if it's a point, it's not
If
a
it's 1
value,
point,
it's a point, it's a
it's a
coordinate.
point. It's a coordinate, right?
An Euclidean
So let's
space.
look at, yeah, let's look at it like 1 point. I just want them to understand, like, look at it as 1 point. What is going to be the value? So if you take 2 minus 2 divided by the total number of points, which is 1, it's going to be 0 over 1. All this squared. I want to show, I'm just trying to establish a relationship between the centroid, the WCSS, and K so that you understand. So assumably, we are saying that if, and since we are saying, because if you have 5 clusters, if you have 1 cluster, you have WCSS, CSS as 1. If you have 2 clusters, you take the WCSS 1 plus WCSS 2, like, because WCSS is the within cluster. So if you have 5 clusters, you calculate the WCSS for this cluster. So WCSS 1, WCSS 2, WCSS 3. So you calculate WCSS for all of them, right? That's how you do it. You calculate, if you have 3 clusters, you calculate WCSS for all the 3 clusters. If you have 1 cluster, you calculate per cluster. So it's within cluster. So it's not like you calculate for this point and then link it with, oh no, it's just per cluster. And so therefore means if we have an agreement on that, for example, now, hey, this guy is not working. If we have an agreement on that, that means here that, let me clean my board a bit, okay? So I don't have a lot of stuff. That will mean that I have 0 here as my WCSS 1, 0 here, 0 here, 0 here, and 0 here. Right? Now let's increase, okay, now that is the maximum value of K, which is K equals to 5. Let's reduce K to 3. If we reduce K to, let's say 2 or 3, for example. Let's say 2, K equals to 2. Let's reduce K from 5. So K was initially equals to 5 and WCSS was equals to 0. Now K equals to 2. What would WCSS be equals to? So now let's see, we are going to form 2 clusters. So we can have 1, 2, 3, 1, 2. So these are going to be our clusters. Is that correct? So we are going to calculate the centroid here. It will be the distance from here to here. So it will be this point, an average of this point, and then you calculate the distance from here to here, and then here. So this distance must be greater than 1, must be greater than 0. Is that true? Yes. Unless I'm the only one seeing it. Who thinks this distance will not be greater than 0? This is WCSS1. If this is your centroid and you have 3 points, who thinks that the distance here would not be greater than 0? Who thinks is greater than 0? Who does not know what to think?
I didn't get the question from the centroid within cluster separation.
I'm saying that are you getting me?
Yes, please.
Initially, our value of K was 5, and
Yes.
the value of WCSS was 0. Is that correct? We agreed on that because we calculated it, right?
Yeah.
Because within cluster distance is going to be 0. That's what I'm saying. Because the point is just 1, so there will be nothing like within 1.
Yes, it'll be 1. Yeah.
You'll be 0.
Distance.
Not, yeah, there will be no distance because how can you say it's a point?
It's a point, yes.
Yeah, so
and the
how
point
can
is
you
itself.
And the point is itself, yeah. So you have a
Yeah.
point like this. How can you calculate within cluster? Because this point is the cluster and it's only 1 point. So there's nothing like within cluster distance. There's no distance. The distance is 0.
Yes.
So we agree
0.
that the within cluster distance when K equals to 5 is 0. That's what we are saying.
Yes. When K equals to the maximum n.
Yes. When K equals to the maximum number of points is 0. It's a fact. Unless somebody disagrees, but that is a fact. Because if I have 5 points, 5 points like this, and each point is a cluster on its own, that means I have 5 clusters. So if I take this cluster and I want to calculate the within distance for this cluster alone, I mean, it's only 1 point. So there's no distance between, it's 1 point. I mean, there's no distance, so it's 0. Literally. So now when we take the number of clusters to be equals to 2, that means we now can have 2 clusters like this. And now we can now calculate the centroid. Here, this will be the centroid. And here, this will be the centroid. Let me mark the centroid with an S, right? This is going to be the centroid. So there will be a distance between this point and the centroid, this point and the centroid, this point and the centroid. And if I calculate the WCSS here, it will be greater than 0. True or false? That's my question.
True. It's going to be true.
It's going to be greater than 0, obviously, right? Because there's actually a
greater
distance.
than 0, yeah.
Yes.
There must be a distance between 2 points.
Yeah. So that means if I reduce the value of K, the value of WCSS will increase because now I'll get a number, maybe say 3, for example. Or let me not just go up to 3 now, it might be smaller than that. Let's say maybe now my value of WCSS will go up to say 1.5, for example. Is that true? Because now there will be a distance here and there will be a distance here. Is that correct?
Yeah, correct.
And therefore means from this we are concluding that if the value of K is increasing, how do you say it? Yeah, I'm increasing with greater than. If the value of K is increasing, WCSS will be reducing. True or false?
True.
It's a fact.
Yeah.
That's a clear fact.
Because increase
So
to K will not equal to the maximum.
Yeah, if you keep going up, K will now be equal to the maximum number of points. Awesome. Okay, now if we have established that, okay, then I'm going to come back here and then I show you. I come back to my elbow method. That means if in your data points you take all your value, you calculate. If you have many clusters, let's say the value of K is reducing. So let's see, if you take the value of K equals to 1, K equals to 2, K equals to 3, K equals to 4, K equals to 5, and then this is the value of K, and WCSS here, WCSS.
See,
so if plot it.
Japhet, don't be disappointed in Daddy. I know Daddy. I'm not surprised at what Daddy has come out with.
So if we take WCSS and then we have K, so if we do a plot, since we know that if WCSS is increasing, this is the maximum, this is WCSS increasing, K will be reducing, you will get a plot like this. At one point, you get something that is called an airball here. This is the point where you can get the best value of K. This is the point where if you use the value of K at this point, you get the best clusters. Is that clear? We want to see this in the practical section. Is that clear? If we do a plot of WCSS against the value of K, against incremented values of K, there'll come a point where you get an elbow, a sharp elbow. You can get more than one. You might get something, you might get something like this, but you'll be able to see one that is clearly distinct. You might get something like this. You might get something like this. Then let's say there's a small elbow here, you come down, then there's another small elbow, there you come down, then there is a sharp elbow like this. You see that at this point, this is the point where the value of K is best to get. That if you now use that value of K for your random value of K, you will have the best clusters. And now if you do the Siloite score, which we already talked about it, which is the Siloite, how do you spell that thing again? Siloite, the Siloite score for that cluster with the value of K that you got from here, you get a good Siloite score. Is there any question?
Prof, I have a question. I want to be sure.
Yes.
So
Mhm.
when we plot WCSS against K, we get this plot that I've drawn, and this
Mhm.
part here, the elbow is going to be our K, right? I hope
Yes,
that's
yes, yes.
okay. I just wanted to be sure.
The corresponding value of K at that elbow is going to be our K value, which is going to be best.
Okay, Prof. Thank you.
That means in that data set, you can get those, if you get those number of clusters, they will be best. Does it make sense?
Yes, Prof.
Okay. For the sake of speed, let's quickly jump into the practical session. Let's see. How many people will be able to follow? This is going to be fast a bit.
I'll be able
If you
to
cannot
follow.
follow, okay. So I'm going to put the packages in the chat and you just follow along, okay? Where's the chat bot? The chat again. Sense. I've sent. Okay. If you don't get anyone, please pip install it. Okay, now. I'm sure. In that our data set, there is this data there called mall customer. Madam Pearl. Under, when you go to the data set, before you don't enter examples, just go under data set and scroll down. You see a CSV file called more customers. Where you dinner? More customers. This is my own. More customers.csv. Madam Pearl, I want to get confirmation that you've seen the CSV file in that folder that I shared with you. Madam Pearl, can I get that confirmation, please?
I've seen it, Prof.
Awesome. Let's proceed then. This is the data we're going to be using for analysis. So I'm going to copy this as path. So let's just show that. So I'm going to have df is equals to EZW underscore CSV, and I'm just gonna pass my row of string here. I'm gonna paste these, and I'm gonna return CF. So the next thing we're going to do is group customers based on, let's see, we'll group them based on annual income and spending score, based on annual income and spending score. That's how we're going to group our customers. So we'll have X, let's just call it X is equals to DF of, for the sake of peace, because I do not want trouble, let me add a cell here and call it df.columns, because I don't want to get
So, are we
errors.
putting along?
I don't know, Dr. Tony, some people are following along. If you can follow along, please kindly do so. If I type any complicated code, I'll share in the chat so that those that are following along can quickly catch up. Like I just shared the packages in the chat, so if you're following, you should be able to see that. So what I've just done here is that I've subsetted, in this data set, I've just removed spending score and annual income, and I've dropped all of this. I've dropped customer ID, January and age. I don't want all of that. So I just want to group my customers. I want to group my customers based on their annual income and their spending score. That's all. I don't need any other thing again. So that's what I'm going to be using to group my customers. Is that clear? Just like in our class example, we were talking about grouping students using their IQ and their marks. I'm going to be grouping my customers using their annual income and their spending score. That makes lots of sense to me. Okay, please let's quickly go. So the next thing we can do, I think, is just to get a scatter plot with
Well,
this.
this is a line of code for X.
It's just this subsetting this. Nothing. Just use double square bracket because we want a data frame. Okay, so let's do plt.scatter. Right, plt.scatter, and then we do X of. So since we don't want trouble, let's just be copying and pasting because I don't want any trouble. We're plotting, let's plot annual income against on the x-axis, and then we plot spending score on the y-axis. Let's spend X of spending score. Hold on. No, this is wrong. Okay. Let's put a semicolon here so that we do not get loose there. Things there. So this is the data. This is the plot. So we have not yet put the plot into clusters, so we don't even know. So this is the plot showing annual income against spending score, right? I don't know, Madam Per, will you be needing this? I'm dropping it in the chat. Okay, let's see. Let's go ahead to group them. Okay, let's go. Let's first of all just what I think we should just do is that let's try to group them using the k-means. So I'm going to say km is equals to, that's what I call km is equals to, then I've imported k-means up here. I'm just creating my argo here. K-means as a function, and if we do shift tab C, n clusters, these are the number of clusters that we have. By default, they are 8. By default, there are 8 clusters. So this is the random value of k. Is that clear?
Yes, bro. Yes, bro.
But we do not know whether this value of k is best because we have not use the elbow method here to see which value of k is best. So by default, the algorithm gives us a random value of k being equals to what? 8. That's what they mean by n clusters. I told you k represents the number of clusters. And so if we do this, there is a formula called, let's just create our clusters. Clusters is equals to, there is a function called km. Km is this one that we have specified here. This is our argo dot fit. There's a function called fit underscore predict. That's the function we're going to be using. And what are we predicting? We are predicting X, which is this data. This data, which shows annual income and spending score, because that is our X. Annual income and spending score, which is what we have plotted down here. So let's group it now and see what the algorithm will show us as our clusters. And so if I do this, I'm going to return clusters to see my clusters. Okay. These are my, it says, it's giving me how many clusters? 8 clusters, because the maximum value here is 7. So, and the smallest value is 0. So it has given me 0, 1, up to 7 clusters. Are you seeing that? So every data point, how many data points did we have in the data set? There are 200 data points. So every data point belongs to a cluster. For example, the first data point belongs to the first cluster. The second data point belongs to the 0 cluster. The third data point belongs to the 6, the fifth cluster, which is 6, of course, because it starts from 0. So, and that I'm going forward. And just to prove it to you, if I get the length of clusters, you see that it should be 200. There should be 200 data points there, meaning that every point belongs to a cluster. So if it's like this, there are 200. Each point, each data point belongs to a cluster. So this is like the case we were talking about. If you decide to do k equals to 200, you would have from 0 to 199, which is going to be your number of clusters, right? But we're not doing that. So, but we have had k equals to 8. So that's why we are having 8 clusters. Who does not understand what I mean by we are having 8 clusters?
Are you saying that this thing I'm looking at now, that says 200, are you saying that it has 8 clusters?
There are 8 clusters.
Okay, is it like the 0, 1 cluster, 1, 1, 1, 1?
This, wait, no, what it means is that there are 8 clusters and they have been identified using number. This 0 indicates the identification of the cluster. For example, if I have 8 clusters, 1, 2, 3, 4, 5, 6, 7, 8. This is the 0 cluster, this is the 1th cluster, this is the 2 cluster, this is the cluster 3, cluster 4, cluster 5, cluster 6, cluster 7, and then cluster 8. But they are supposed to be 8, not 7.
So they are indexed from 0, not 1.
Yeah,
Indexed
that's
from 0,
not
yeah.
1. So it ends at 7. Dr. Tony, do you understand? Now, within each cluster, there are points inside each cluster. For example, the first point on our data, assumably, if I have to be very critical in my thinking, this 0 point, this point 1539 says it is in the first cluster, in cluster 1. I don't know where is cluster 1. Maybe this is cluster 1. Maybe this is cluster 1. But it says it's in the first, in 0, in the second cluster, which is the cluster number 1. This one belongs to the 0 cluster, which is the first cluster. This one belongs to the 5th cluster, the 7th cluster, which is cluster number 6. This one belongs to the 0th cluster. Dr. Tony, is that clear?
Maybe as time goes on now.
It's simple. We have 200 points, and these 200 points have been divided into 8 clusters. Simple, right? 200 points divided into 8 clusters. So each point finds itself in a cluster. Make sense?
Yeah, a cluster is a group of points, group of data points.
As you can see here, 0 comes how many times? 1, 2, 3, 4, 5, 6, 7, many times.
Prof, meaning that these numbers represent the index of the clusters.
Yes.
Okay.
If I ask you how many people are in cluster 0, for example, if I get the length, I don't know if can I do this of
So do unique
uh,
values or
I'm just thinking of doing equal 0 or something like that. Let me get the length of clusters. Let me do this. I don't know if it's going to work. Clusters equal 0. I don't know if this is going to work. Yeah, no, this is not. This is not giving me the vibe. I need to have a different way. Let me do x cluster equals 0. There are 21 points in the cluster 0. In the cluster 0. You see that? That means if you come here, out of the 200 points, 21 of them are in that cluster 0. How many are in cluster 7? How many are in cluster 5? How many are in cluster 1? How many are in cluster 2? How many are in cluster 4? How many are in cluster 3? So we have 8 clusters altogether. Is that clear? Okay, since you're having challenges, I think we can plot the clusters. I think that should be possible. So we can do something like PLT dot scatter. And if we do PLT dot scatter, I'm going to do, so let me just pick these. Let me start with 0, right? X of 0, and I want, on the x-axis, I want the annual income of X of 0. I want the annual income of X of 0. And then comma on the y-axis, see, I want the spending score of X of 0. So all the points that say they are they are in cluster 0, I want to plot their annual incomes against their spending scores. So if I do this, so if I run this one, it should give me a plot, of course. Yeah, it gives me a plot. But this is not all I need. I have up to 7 clusters, so I need to plot all the points. So I'm going to copy this and paste 6 times. 2, 3, 4, 5, 6, 7. Should be 8 now, 8 times because there are 8 clusters. So 0 works. The next one is going to be 1. This is for cluster 1. Then this should be for cluster 2. Then this should be for cluster 3. Right? It should be for cluster number 4. Cluster number 4. It should give me cluster 5. I hope I've not repeated anyone. 6, 6, 7, 7, and we have 8 clusters altogether. So if we plot this, I should see 8 clusters. Oh, perfect. Dr. Tony, now do you see the 8 clusters? Huh?
Yes, I see them.
Okay. So these are the clusters. So now, but we do not know. And so one thing we want to know, we can measure how good these clusters are. Is that possible? Is that so that's correct, right? We can measure how good these clusters are. So How do we do that? We run a Siloite score. That is, we already agreed on that. So if I, oh, Madame Père, sorry for putting you in trouble. I know you're struggling on the background, struggling to type this thing that I've typed here, but I did not type it. I actually did copy and paste. So I will just copy it and paste it and change the numbers.
Thank you, Prof.
So yes, so we can do a Siloite score. I think there is an H somewhere. Yeah, there's Siloite. I think I even imported it right, just to be sure that I don't spell something wrong. This is it. I imported it here. I mean, this is Siloite is not my name. I'm suspecting it's the name of the person who discovered this thing. So let's get a Siloite score of X. Again, there is a function called, there is a parameter called k-means dot labels on the score. So if we run this Siloite score, it should give us, oh, label, is it labels? Labels. Yes. Okay. You see, and I told you the Siloite score runs from -1 to 1, right? So our Siloite score has given us 0.4, approximately 0.5, right? That means it's still away from 1. Let's see whether we can improve it by getting a better value of K. This tells you the quality of your clusters, how good your clusters are. And how good your clusters are is just a mere representation of the inter and intra distance. This is inter distance, and then this is intra distance. No, sorry, I'm mixing it up. Sorry, don't go there. This is the intra distance, which was A in our Siloite score formula, and this is the inter distance, which is B, right? So this is A and this is B. So distance between this cluster and this cluster, a point on this cluster. So if you take this point to this point, it will be this point to this point, this point to this point, this point to this point, each point to this to this. So the distance between a reference point and all other points on that in the next cluster, this will give you the value of B, and we always take the mean. So whichever one is the best from all the clusters, that should be used to calculate the Siloite score. So the value of your Siloite score just tells you how good your clusters are. And we said if your Siloite score is 1, that means your clusters are really good, right? Okay, now, are we together?
Yes, Prof. We're together.
Okay, awesome. So let's do something a little bit extra. So now we do not know whether this value of K that we used over here being equals to A gives us better clusters. I'm not sure, you are not sure, because it was a random value. So let's see if we use the elbow method, we're gonna get a better value for K. So let's use WCSS being equals to, let's just hold the values of WCSS in a list. And now let's assume, let's just take 16. Let's just say we are dealing with 15 or 16. Let's say 15 clusters, for example. So we are going to say for I in range. For I in range, let's start from 1 because I don't want to use 0. For I in range 1 to 15 because it's 16. So if we are saying 15, so 16 is n minus 1. For I in range, so we are talking about 15 clusters. So we are just assuming that our best value of K will lie in between 1 cluster to 15 clusters. That's what I'm saying. The value of K will lie somewhere here. If you like, if you have a good computing power, you can take this to 200. It's up to you. But me, I'm going to end at 15. So nobody should attack me. You can take your own to from what I in range 1 to 200 because there are 200 scores. That means you are using K equals to N. For I in range, you start from the beginning till the last value.
where because your maximum value of K can always be equal to the number of records. So if you like to go up to 200, it's up to you. But me, I'm going to end at 16, okay? Hope that's clear. So I'm just assuming that my value, the best value of K should be between 1 to 15 clusters, but I don't know what the value is going to be. That's what I'm saying. So for I in range 1 to 16, so let's use, so we're going to come here and say, I'm not going to, let me not override the value of km here. So I'm still going to use this, but instead of using km this time, I'm just going to call it k-means. Instead of using km, I'm just going to call it k-means, okay? I don't want to override km because I'll still use it. So I'll say k-means. What are you doing? Excuse me, let me. K-means should be equals to km, and then shift up. The n clusters should be equals to I. Let me copy all of this. N cluster should be equals to I. So what I'm saying is that if I start in the range 1 to 16, the first time this loop is running, it's going to use the value of clusters, the value of K to be equals to 1 when it starts from 1. When it goes, the loop runs the first time. The second time, the value of I will go up to 2. So it will use 2 clusters. The third time, the value of I will go up to 3. So we use 3 clusters. And for each of these times that this thing runs, I want to get the value of WCSS. For each time, I want to get the value of WCSS. So what I'm going to do is that I'm going to do, so after you do that, I'll do k-means dot, let's just fit and not predict, let's just fit x. And then, and after fitting, now I get the value of WCSS. So I'll use WCSS dot append. There is a value in K, there's the value of k-means is stored in the value of the WCSS is stored in the function, in the parameter called k-means dot inertia. So you are getting the inertia. I told you it's also called inertia, so you can do it. So if you run this for every time you run a prediction, you'll get the inertia. So if I do this, so let's see, for example, when we use this one, what was the inertia? Can I? Okay, let me run this. So if I do km dot inertia underscore, you see the value of the inertia when our cluster was equals to 8, when the value of k was equals to 8, the value of WCSS was 209, 200, what's this? 200 and, what's this?
29,000.
29,032, sorry. 29,032, that was the value of inertia. Point this was the value of inertia. So what I'm saying is that for each time that this loop runs, we want to get the inertia value. That's what I use WCSS dot append inertia. K means of inertia. So if I get that value of inertia, I'll now plot it against my values of K. So what is my WCSS? If I run this, you see.
Well, does
these are
the
my
value
values.
of inertia depend on something? Because my value is
It
different.
depends on the value of K. We already agreed that. We already illustrated that, right? That if your K equals to N, inertia is 0. When you reduce the value of K, your value of inertia increases. So it depends on the value of K.
Okay.
We proved that now, Madam Pearl. Were you not here when we were plotting, when we were saying?
Oh, is that what we're plotting?
So that should tell you that your inertia is being influenced by your value of K. Very, very important.
Okay.
That's why for each value of K that we have here, for all the 15 values of K that we have tested here, we have different values of inertia. Can you see that? And so if for you, you used, instead of 16, you used 201. you have 200 values of inertia inside here. I mean, for the people who have big computers like Dr. Tony, that can run a loop of 200. Hey, Dr. Tony. Any questions so far? So this is our WCSS. So we can plot now. We can do plt.plot, Abi. And so that we get the value of the point where the value of k is. We get a point where, so plt.plot. plt.plot on the x-axis, we want to actually get our value of k. So I'll use a list function to convert the range function to a list, because this will only take a list. So I'll do range 1 to 16. I hope you people know what this result will be. For my people who have forgotten, if I run list range 1 to 16, I'll get 1 to 15. You see? So these are the values I'm plotting on my x-axis. This is just for the sake of clarity, so that there should be no confusion. So this is going to be it on my x-axis, and on my y-axis, I'm going to have my WCSS. And then I'm going to do plt.xlabel so that we don't get confused. Xlabel is going to be k, of course, the value of k, and plt.ylabel. Ylabel is going to be WCSS. And so if I run this, okay, let's see. And so I see that if I look at this carefully, I see that my best value of k is on this elbow here, somewhere around k equals to 5. Is that true? Is that true?
Yes, bro.
We can see now the sharp elbow is around k equals to 5. So that means we'll have better clusters when we use our value of k being equals to 5. And so if that is the case, then okay, now that you have given me the value of k, thank you for giving me the value of k. I'm just going to come up here and I'm just going to copy this. And I'll come down. But Ampere, do you need anything from me?
No, Prof. I have all the
Okay. So if I come down here, I'm going to paste this and I'll do shift tab inside here and I change my value of n clusters to be equals to 5. Because that's what the above method tells me. So here I'm going to use 5. Simple as that. And if I run this, I now have 5 clusters. 0 to 4. I have 5 clusters. And if I have 5 clusters, I might want to see the 5 clusters. So I'm going to come back and copy this. I don't need up to. So I just copy this to 4, right? I don't need all of them. I just need the first 5, which is 0 to 4. Because I'm not using 8 clusters again. So I'm just going to paste this here. Put a semicolon here and run it. Boom, I have 5 clusters. These are the new 5 clusters. And if these are my 5 clusters, I might want to see the value of Siluetes score, whether it has changed. Oh yeah. So let me get my value of Siluetes score. I'm going to run it again. And if I run this, oh, it has gone up from 0.4 to 0.5. Has it improved? So maybe if we run this again, maybe if we run from a range from 1 to 200, maybe we would have get the best value of k somewhere over there, around 100 or so. I don't know. Something that you can keep twirling.
That your elbow is the issue now.
Pardon?
That the optimal point at the elbow, which you are trying to optimize the less clusters. We choose 5 here. But if you look at it, is
Mhm.
it smoothing out? Is it flat? Has it played two? It has not actually played two. It's played around that kind of 9. Like 10. I
Around
think
9.
10 is like the play two there. So 10. Look at 10.
Okay.
So
Let's
you see
try
that 10.
let's try 9, for example. He's saying we should use this point. That's what Bestman is saying. Saying we should use this point. So let's this airball down here. So let's try. Whether we'll get a better value. Maybe we'll learn. So I'm gonna bring this down, and instead of 5, I'm gonna use a 9. 9 clusters. So if I run this, boom, I get 9 clusters. And if I get 9 clusters, then do I need to see the clusters? Let me just check my seniority score directly. Do we get a better seniority score? Ooh, our seniority score drops instead. Is that true?
True.
So I think we got the optimum value where we have our airball being very sharp, around 5. Remember, we first of all used k equals to 8 and we had 0.4 something. So, are there any questions? Are there any questions? Dr. Tony, did
I have a
you,
question.
yes, Madam Pearl.
Yes. For this point that we traced or we extrapolated to be 5, is it possible to get the exact value from the plot?
Oh, la, la. If you, I don't know, maybe you add grid lines and then reduce the, maybe set the step size here to 0.1. Madam Pearl.
Yes.
You add
So,
grid lines to the plot and set the step size here to 0.1. That way
we
you will make
won.
this thing very granular.
Like, okay, so I thought that was an easier way, but okay, no
But I
problem.
think you cannot, I don't think the value of k can be float value. It should be an integer. I don't think you
Really?
can take a float value. Yeah, I don't think you should be able to take a float value. Let's see. I'm not sure. I'm not sure. I mean, it should be an integer. Doesn't make sense. But do you think it should make sense to be a float value?
Cannot be a float value now. A point is a
Cannot be.
cluster is a real number.
It's a real number, right? So I think if you put a float value here, it will throw you off. It's a int. So it must be an integer. Madam Perry, do you understand what I'm saying?
Yes, bro.
And so if your value of k must be an integer, and then the question you are going to now ask yourself is, looking at our elbow over here, what is the integer between 4 and 6?
Obviously 5.
Thank you. When you added the part that obviously it made my life sweet.
Okay.
Are there any other questions? Dr. Tony, are you still on the call? I think this is one of the simplest algorithms we've looked at.
Yes, I'm on the call.
This is one of the simplest algorithms we've looked at, right? Very straightforward. Nothing there. I mean, if you look at this compared to some algorithms, so look at an algorithm like SVM. I was really wondering whether I should teach SVM. Start talking about those margins and crazy stuff. But we're gonna look at some of those algorithms once we are done. I'll just take those crazy algorithms and we look at them. Like SVM, naive bias, that one uses Bayesian analysis. It works with probabilities. I like Bayesian analysis. It's actually really cool. I think I prefer the Bayesian approach to the frequencies approach. Bestman, I don't know your take on that, but I think
Naive Bay. Yeah,
yeah, I think
Bayesian
I prefer the
is more than
I
it's
think I
more
prefer the
it's better than
Bayesian
these
analysis to
frequencies.
data approach than the frequencies approach.
Yeah, I think Bayesian is modern than frequencies. Frequencies to be the
And-
classic statistics.
And it makes it makes more sense.
Yeah, Bayesian makes more sense. And it's more
I mean,
robust.
you can explain data better with probabilities than telling me about p-values.
And this can update itself based on observation
Yeah.
on the statistics and what is being observed to observe.
And just to think that your outcome does not really matter on the prior. So your prior can be anything. Think of
Yes.
anything.
Yes.
It's actually
Visualize
nice.
it.
And then, you know, the most exciting part is the fact that it takes into account experience. Because you can
Yes.
choose a better prior based
Domain
on
knowledge.
Yeah. I like it. I used it for, there was this advanced analysis for PhD that we did some time back. And it was so complex that I had to use the Bayesian approach, even though the university was strongly recommending the frequencies approach, but we had to deliberate a whole lot because we could not explain the outcome of that data better using the Bayesian, the frequencies approach.
Frequencies.
Yeah, it was just so out of place. I mean, you see values, but you cannot tie those values to a logical explanation. It's kind of crazy though, but I mean, it's actually interesting. You know, if we have time, we can look at some of these very cool things about that. Statistics is nice. We can look at some of these cool stories around statistics and play around with them. Get to enjoy, you know.
Did you take a look at this dendrogram in determining the number of clusters? Dendrogram. You know, you came in is one of such. When it's not clear, you can also use dendrogram.
Okay. Any other queries or worries? If not, please let's call it a day today. Let me rest
This
my
initial,
head.
can you share the formula? I know this initial has to do with the cost function in terms of the momentum builds. I don't know. You have the, I can't remember the formulation. For this initial.
We were looking at it here, right? See, we were looking at it here, and we were looking at. I was just worried why the guys were just wrapping the thing around multiple. Like you see, look at what we have here. This is k-means explained, right? K-means being explained, and okay, you just imagine yourself calculating the. This is where that's just some explanation. I'm looking at where calculate the inertia. No. Global optimization method and decision. Let's see where they calculate the inertia. Nobody is calculating inertia. I think I put up a. Okay, this was the CSS formula. I was just looking at. Okay, let me pull up this one. This was the one I opened, I think so. And I was just. For some reason, these people are saying I should verify my IP address. Are you crazy or something? Wow. Once I visit your crazy website, that's why you're giving me. Okay. You see what I was showing you people, guys. You see, based on how you're just looking at this is the formula for the calculation of inertia, right? This is the formula for calculation of inertia. And you see, it's clearly explained here. As you can see here that this xi minus j just gives you the difference between the data point and the centroid. The centroid of your cluster. I was just wondering why they actually use double absolute value squared again. I mean, and then I was Googling it, and they said it's something about historical fact and blah, 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 blah.
That is the Euclidean, is that not the Euclidean distance? Those double
If
lines.
the Euclidean distance was supposed to have a square to cancel out with this, so it's not a Euclidean distance. We're supposed to have a square root to cancel out with
A square is to normalize it now. It's
And
to
that's my question
standardize it,
is you
to
why
normalize
are you
it. So,
standardizing it if you use the absolute? Using the absolute
no,
is saying that you are taking the magnitude, right?
no, absolute
That's
value is that one without the sign. There's no plus, there's no minus. It's just the
that's
value
what
as
I'm saying.
itself.
Why are they using double bar? Why double bar?
It's to show that is the distance from xi to cj at the Euclidean distance. No, we have many distance. We have Homo habilis distance. We have cosine distances.
And then
So this one is the
Monchowski
Euclidean
or
distance in space. So it's just normal from like it takes cognizance of the sign. So if this x is on a negative intersect, it's going to reflect. But if it has to do with Manhattan distance, then that one is absolute value. You don't need this. So this is to show that it's Euclidean distance, the norm square is more like difference between x points against the centroid that is determined. Then for each number, it would to iterate it for each number for that x points from each point to the centroid, and for each cluster, like it's going to be a two-dimensional check from that centroid to each point around that centroid, then from that point to other clusters to see the one that is closest. And this is the Euclidean distance. Those double line. You
so
see
if you
distance, see
were
it under there. I
asking,
wrote distance.
yeah,
You don't have the initial. The initial is not yet. This is just the. Can you see the
another
initial?
name for WCSS is inertia. It's also called inertia.
Within cluster, square, sum of squares.
Yeah, within cluster square sum. It's also called inertia. So this you can call it WCSS or you call it the inertia. It's up to you. Okay. Any other worries again? If not, please let me rest. Okay. I have severe headache.
Thank you.
So
Prof.
we'll have our next class
Passion.
on Thursday. Thank you. We'll have our next class on Thursday. And in a few 2 or 3 classes, we should round up with machine learning, and then we start SQL. And just to remind you, if you have not downloaded that desktop SQL, we started doing that at a point when we were still doing Python. If you have not downloaded it, please make sure you download it, because we're going to be working on that for our SQL practical session. I'm going to be using that interface for writing SQL queries. I'm not going to go anywhere else, please. I don't want to start installing connectors on my computer left and right. So please make sure you have that stored on your computer. Is that okay? Because very soon we'll be going into SQL. We are almost done with machine learning. We are not doing unsupervised learning. Very few algorithms here. I'll just look at another 2 or 3 algorithms on our unsupervised learning. We trash it and we good.
Or we use SQLite.
Bro, let's just use the desktop. I mean,
Okay.
it's
Industry
easy
standard.
to extend from there. Because the problem, I just don't like teaching from an interface without from a system without an interface, because there are certain things that people can see them better when you are showing them. Because one thing I like about the SQL desktop is that if I create a database, I can actually show you that this is the database, and then you actually see the subset showing the tables, the database, and then it's makes more
Graphic
sense.
user interface. UI.
Yeah,
But as
when you have a
programmers, you want to
graphic.
be back end now. You want to work with codes. You don't bother with those
But from
fancy
the teaching point, my problem is teaching. When you are teaching and you are telling people these things, and especially people who are not coming from a purely IT background, it becomes difficult for them to comprehend it if you're not showing them something, right? It's really challenging. So it's preferable let's do it from a graphical interface, which in
Yes, sir.
most cases, when you find yourself within working environments, you have those graphical user interfaces there to work with. So I mean, it's not a bad idea, right? Unless you want to go hardcore, that's when you start writing with CLIs and all of that. But I mean, those interfaces are always there. They know that. Okay. Let me also leave those who want to watch football to go and watch Barcelona and Borussia Dortmund. Okay. Here, my Barcelona fans. Good night.
Hi, Prof.
Nice. We win.
Yeah.